Okay, so we are recording now. We are moving into section 11.4, tangent planes and linear approximations. And I'm going to just read from the paragraph. One of the most important ideas in calculus is that as you zoom in towards a point on the graph of a function, the graph becomes indistinguishable from its tangent line. In other words, we can approximate the function at that point by a linear function, so long as we restrict our attention to very close to the point. Here we develop similar ideas in 3 dimensions. As we zoom in towards a point on a surface, that is the graph of a differentiable function of 2 variables, the surface looks more and more like a plane. Okay, and so to see this, let me just hold on, I don't want that. One moment. Yeah. So here they have in figure 2 an elliptical, and this actually goes with the first example, but I just wanted to show you. They have a paraboloid, and it looks like a bowl. And in these figures, in figure 2, they have an A, B, and C. So if you go from A to B to C, what are they doing? They're zooming in on the point 1, 1, 3. If you look at the X and Y axes, so in figure 2A, the y-axis goes from -4 to 4, and x-axis goes from -4 to 4. In B, they tighten the y-axis to go from -2 to 2, and the x-axis to go from -2 to 2. And then in C, they even go more. You know, the x-axis goes from 0 to 2, the y-axis goes from 0 to 2. And you start seeing as you zoom in towards that point on the surface, 1, 1, 3, it's on that paraboloid. The paraboloid starts looking like a tangent plane. So the question is, can we come up with a tangent plane? And the answer is yes. The answer is yes. So the book goes through a derivation, but I want to just sort of work with you just directly, and we can try to use our intuition a little bit. A lot of the multivariable calculus concepts are extensions of single variable calculus concepts. So for like, okay, so like if you have a function of one variable, how do you remember this formula? And I'll use approximately here. This is a linear approximation. Okay, we're taking our function here and we're approximating it by a line. So a line, remember, a line has the equation y equals mx plus b, right? So here's the derivative at a point. That's your slope. Okay. And I mean, how does this hopefully rings a bell. This is a linear approximation of a function x at the point x equals x sub 0. Give me a thumbs up if you recall this. It's been a little while, but hopefully some of you recall this. Okay, good. Abdullah, Yeva, Alberto, good, good, good. Wonderful. And Aura, and you know, you could also rewrite this as like f of x equals f of a plus f prime of a times x minus a. How many remember that? Like a Maclaurin polynomial. Maclaurin polynomial of yeah, that's that's like your good. And thank you for those that I tried. I think who answered there? One moment. I always like to acknowledge people that answer. Norina and Ara. Yes, very good. So this is like well, it's a linear approximation. Now, let's say that you want a linear approximation of a function of two variables at well, I'll tell you what, let me just alter this a little bit. Okay, let's say, well, hold on. No, one moment. No, we'll stick with it. We'll stick with this. This is fine. Okay, but we also said at x equals a, right? For the second, for you know, this first part here. Now we could also find a linear approximation of a function f of x y at x equals x sub 0 and y equals y sub 0. So if we were to do that, the formula, well, so here we had an f of x sub 0. So I imagine here we're going to have an f of x sub 0, y sub 0. Right? Seems to make sense. And then here we had the derivative at x sub 0. Well, we're going to have a derivative too at x sub 0, y sub 0, but it's the first partial derivative with respect to x. So this part here corresponds to this part here. But do you think we're done? Do you think we're done with this linear approximation formula? Do you think we're done with it? Or do you think there's another part? There's another partial derivative. Partial derivative of f with respect to, this is an extension, right? Of this formula. So partial derivative with respect to y. See? So and sometimes, by the way, we'll call f of x z and f of x naught y naught z sub 0. But the point is, you get the equation that, what is this? This is a plane. It's a plane. It fits the format for a plane. And if you want to, oh, I have one thing wrong here. this should be f of x comma y. All right, so we could also, by the way, write out, if we wanted, if we wanted to use, instead of x and y, we wanted to use a and b, we could. You know, we would just, I'm sorry, no, that's not right. That's not right. What I'm saying is, no, we need the x and the y here. But we could replace x sub 0, y sub 0 with a and b. So you're going to see it in different ways. Okay, so you know, second formula here, right? So okay, now let's go to the book and yeah, I think everything looks good here. Let's go to the book. And let's go up here. One moment, class. So there's the one formula I mentioned to you, right? There's the one formula. We also think of this linear approximation as what they call a linearization. That's another way to think of it. But let's look at an example here. Example 1 says find the tangent plane to this elliptical paraboloid at the point 113. So all we need to do is compute these compute those two partial derivatives, evaluate them at the point 1, 1. Not hard. And then we'll get the equation of that tangent plane by using the formula. And that tangent plane, okay, I mean, hopefully there are no questions. It's really just that you can write that tangent plane I mean, this is the, hold on. This is the tangent plane, but you can write it simplified this way. And, you know, there's a picture of the paraboloid with that tangent plane. And you can, you know, you can do a nice check and you can see it works. Okay, are there any questions on that? All right, hold on. All right, R is good, very good. Let's move forward then. So the book sometimes likes to use this notation for a linear approximation. Again, it's a first degree Maclaurin polynomial, but for a function of two variables. It's a linear approximation. And you can see below that that's more how I like it, the way they write it below in Formula 4. Okay, so these, and by the way, this can be extended. Hold on here. This concept. Let me just go forward here. There's a lot of good stuff in this section. Forgive me, I'm trying to find the formula I'm looking for here. Nope, that's not it. Hold on one moment, I'll find it. Yeah, there it is. How about that, class? You can find the linear approximation for a function of 3 variables if you wanted. But it would involve 3 partial derivatives. See that? It's just an extension. And if you had a function of 4 variables, the linear approximation would involve 4 partial derivatives. But it's all an extension of the linear approximation to a function that you learned back in Calculus 1 and Calculus 2. Okay, now another thing that we can talk about here in section 11.4 is tangent planes to parametric surfaces. So again, surfaces like cylinders, for instance, you need to, if you're going to graph that cylinder, you need to use a parametric a vector function with 2 parameters. So what if you had a situation where you needed to find the tangent plane? Well, if you had 2 surfaces, no, if you had a surface like this, that's not a function of x. You can't express the surface as a function of x and y. So the formulas that you just saw wouldn't apply directly. But yet you have a surface. You could have a point on this surface, and there's a tangent plane to the point. How are you going to find the equation of the tangent plane? Okay, and again, graphically, well, this is the situation we're dealing with in Figure 9. So you have there in Figure 9 a surface, and you have a point on the surface, and if you were to draw the 2 tangent vectors to that point on the surface, okay, the 2 tangent vectors would be r sub u and r sub v. So those are the derivative vectors. Okay, the derivative vectors, I mean, they have r sub v up here. Okay, that's where let me just kind of highlight it here. So if you hold the 1 parameter constant, if you hold the parameter u constant, and find the derivative vector with respect to v, then that tangent vector would be the tangent vector that you see in Figure 9 here. See in Figure 9? I want to say this the right way. Just give me one moment. One moment. So the r sub v is the tangent vector to the curve C1. One moment. I might have this. One moment. Um, I'm wondering, I'm just checking, double checking that picture, actually. So you have a point on a surface, and you have two space curves to the surface. One space curve corresponds to holding the parameter u constant in figure 9. The other space curve, that's the C2 space curve. Yes. And then the C1 space curve is when you hold the, well, no, let me say that again. So the C1 space curve is when you hold one parameter constant. Okay, and that's that you're holding the u parameter constant, so you're differentiating r with respect to v. And then the other space curve, the C2, that there you're holding the variable v constant, and so you're finding the derivative vector r with respect to u. Yeah, that's fine. That's fine. So if we were to come up with these two derivative vectors and take their cross product, that would give us then the normal vector to the plane containing those two derivative vectors in figure 9. And if we have that, we can find the equation of the plane. There's the, by the way, there's the derivative vector with respect to u. You just differentiate the components with respect to u. So really then, if we look like at example 7, okay, if we look at example 7, and I'm going to do it in the book because I'd like to try to give you some time to work a little time, but they say find the equation of the tangent plane to the surface with these three parametric equations at the point 113. So what they do is they find the two derivative vectors. So take a look, two derivative vectors. So the derivative vector of r with respect to u, they're holding v constant. So you get the derivative vector 2ui plus 1k. And then the derivative vector r with respect to v, you're holding the u constant. So, you know, those parametric equations that are highlighted in yellow above, if you differentiate each of those parametric equations with respect to v, you're holding the u constant. That's going to give you 2v times j plus 2k. So the next step then, and by the way, here's a picture. Here's a picture of what's going on. There's that surface, and there's the tangent plane we're looking for. Okay, so let's find that tangent plane. So, okay, we have the derivative vectors. Now we take the cross product of those derivative vectors, and that will give us the vector negative 2vi minus 4uj plus 4uvk. Now, incidentally, if you did the cross product if you did r sub v cross r sub u, you would just get the negative of that vector. So, you know, one normal vector will point upward from the plane containing those two derivative vectors. The normal vector, which would correspond to the cross product in the opposite order, that will correspond to the other normal vector pointing like downward from but below the equation, below the plane. Okay, so it doesn't matter which you do. Now what they do is they say, okay, notice that the point 113 here, I'd like to try to highlight this. Notice that the point 113 corresponds to the parameter values u equals 1 and v equals 1. Well, that makes sense because if you look at 113 and then look at x, y, and z, your parametric equations for this surface, well, u and v would have to be 1. I mean, there's no other way no other way that point would be on that surface. It's on the surface, 113 is on the surface when for u equals 1 and v equals 1. So in other words, when u equals 1 and v equals 1, if you were to draw the position vector with those components x, y, and z, it would touch 113. So, okay, now all we need to do is in this cross product vector above, just substitute in u equals 1 and v equals 1, and you'll get the normal vector negative 2i minus 4j plus 4k. It's really quite beautiful, really. You'll get, whoops, not a flashcard. I don't know what that is. Hold on. You'll get this. And then now you just go ahead and get your equation of the plane, because you have the normal vector to the plane, and you have a point on the plane, and you're good to go. So that's the procedure. That's the procedure. And incidentally, it would be nice to see if you know, like let's say you're, you know, when you're doing your homework, or maybe you're doing a problem like this on an exam. I mean, it would be nice to be able to produce a graph like you see here in figure 10. And I have a program I wrote that it's actually for this particular example that will produce this graph. Well, or something like this. Again, the goal is, can we graphically verify our answer? And the answer is yes. So it's if you go into, let's see here, if you go into, let me see, one moment. Really quite fascinating. Yeah, if you go into the Blackboard and click on MATLAB Programs, okay, and then click on the module, and then click 11.4. Please click on that MATLAB program, open it up, and the code, then take the code and paste it into MATLAB. So take a moment and do that. Is everybody seeing this? Is the program opening? When you click on the link, is it opening? Okay, good, Yeva. Good. Okay, so try this now. Try this. And let me see here. Boom, boom, boom. You should have this code. Now, we're going to define our symbolic variables, u and v, and we have to use the hold on command, because we're going to graph that funny looking surface, and then we're going to say, hold on, MATLAB, I have a second surface I want to graph. So the parametric equations for the first surface are the ones that you see in example 7 from section 11.4. But what's going on with the parametric equations for the second surface? Well, let me show you that. Let me go to the whiteboard. Here it is. Okay, so for this example 7, the equation of the tangent plane, well, it turned out to be x plus 2y minus 2z. Let me write that a little better. I can do better than that. X plus 2y minus 2z plus 3 equals 0. And you could express this as x equals negative 2y plus 2z minus 3. I mean, you could, right? You could. And if you did that, then you could say, okay, well, so what are the parametric equations? Parametric equations for I can do better than that, for this plane. I mean, here's the plane. So the parametric equations, of course, you have an x, y, and z, and each of them are functions of your parameters, u and v. And because I wrote the equation, the plane equation, as x equals a function of u of y and z, I'm going to let y equal u and z equals v. I can do that. Well, this means then that x will equal negative 2u plus 2v minus 3. So in short, x equals, well, I'll write it as negative 3 minus 2u plus 2v. Y equals u, and z equals v. And that's what you're seeing. One moment here. Yeah, that's what you're seeing. Sorry. One moment. Let's make that a little nicer. That's a V. Yeah, this is exactly what you're seeing in the code. Okay. So, and by the way, you could have done it differently. I just wrote the equation as the plane as x equals because x was by itself. But if you wanted to like divide everything in the equation here by 2 and write z equals a function of x and y, you could let x and y be u and v, and then z would be, you know, the other equation. I mean, parametric equations are not unique. So, but on that note now, here we are. And I'm going to copy and paste the code. Okay, I'm going to copy. So I see on the right, there's warning signs, but it's not like red. So it's not like the program won't run. And I see, you know, so easy surf, there are more modern commands in MATLAB, but look, it works. They talk about using fsurf, that's fine. But you know, I'm gonna use easy surf. I'm gonna use that command because it makes sense to me. It's easy to graph a surface. Easy surf, I like it, and it works in MATLAB still. So let's just use it. All right. I'm going to copy the code, paste it on the command line. I might do clear variables first, just to clear out all old variables. Then I'll paste it on there. By the way, I'm letting the u parameter go from -2 to 2, and the v parameter to go from -2 to 2. Okay, and you should get a graph. It ran. So let's get the graph up. How many are getting something like that? Good, good. You're getting something like that. Eva is. Is there another, maybe a few other people getting that? Okay, wonderful. Angela and Norina. Okay. So, and Lexi, wonderful, wonderful. So I'll go to tools. Thank you. Thank you. I'll do a rotate. I just want to, it's hard to kind of see the tangent part, but if I rotate things around, yeah, I mean, it's 3 dimensions, right? It's what I mean is it looks like there's a little space there, right? But it's tangent. I mean, there I have a pretty good view and can see its tangent. That's a graphical confirmation. So this is basically, these are the concepts behind section 11.4. And are there, and remember, we use linear approximations. We use linear approximations to find approximate values of functions. That's what we use linear approximations for. And we're just doing it here. Like example 2 talks about, let me just see here. Maybe I'll just get that in real quick. So this is fine. Let me go to the book. I think this material, kind of this nice guided tour is good enough for this section. But let me just, sorry, I just got to get there. Yeah, this will do. So in example 2, they want you to use linearization to estimate a function value. And again, all this came up because when you think about like mathematicians hundreds of years ago, they had to estimate these function values, and they didn't have computers, so they had to find ways to, use approximations to estimate these function values, and the approximations involve, these basically the terms of a polynomial involve addition, subtraction, multiplication, and division, which you can do, and a computer can do that, by the way, also, right? Those are flop operations. So we can, how does a computer estimate a function value? Okay, it surely it uses approximations at least at certain times, right? So okay, so we have this function. We want to find. Hold on. Yeah. Find its linearization, then use it to approximate the function at the point 1, negative 0.1. Now you notice they're using the value 1, 0. That's because when you compute the partial derivatives, okay, the partial derivatives are easily computed when x equals 1 and y equals 0. And if you recall Maclaurin series and Taylor series back in Calculus 2, you were always Maclaurin and Taylor polynomials back in Calculus 2, you were always expanding those polynomials around nice values where the derivatives could be easily computed. It's the same here. You want to expand your polynomial, or you want to, when you do your linearization, you want to have expand around a coordinate that's easy for you to compute the partial derivatives, and that's why 1, 0 was chosen. So now you can do the linearization, okay, using the formula that it's intuitive, that formula, so the corresponding linear approximation then is what you see then here, that x times e to the y power x times e to the xy power, which is a complicated function, it can be approximated by this very easy function, x plus y. So long as you're maintaining your focus around the around points where close to x equals 1 and y equals 0. So they evaluate the function using the linear approximation. I mean, look how easy that is. Look how easy that is. F of 1.1 comma negative 0.1. 1.1 is close to x equals 1. Negative 0.1 is close to y equals 0. Using the linear approximation, it's just 1.1 minus 0.1, and you get 1. Now, the actual value is 0.98542. So, it's off a little bit, but hey, that's not bad. That's not bad for, a linear approximation. And that's how you use this, these ideas. Are there any questions before I stop the recording? Okay, who's feeling reasonably good? Reasonably good? All right, Angela, very good. Abdullah, excellent. Marina, good. And Yeva? All right, wonderful, wonderful. Well, let me go ahead and stop the recording. We've covered section 11.4 now. Excellent.